Welcome to this talk on automatic inference of search patterns for taint-style vulnerabilities. My name is Fabian Yamaguchi, and what I'm about to present is joint work with Alvin Meyer, Hugo Gascon, and Konrad Rieck, and we're all from the University of Göttingen in Germany. So before we talk about automatically inferring anything, let's take a look at what taint-style vulnerability is. So this is a common theme that's been popping up in recent research papers on vulnerability discovery. And the idea is that there's some sort of attacker-controlled source, and the data from this attacker-controlled source propagates to a sensitive sink, and there's some sort of check missing, right? And fortunately for us, there are prominent vulnerabilities with logos that are examples of these kinds of bugs. So for example, the heartbleed vulnerability that you see here in the back, that's a good example. So here you have this flow from function n to s to the third argument of a memcopy operation. And in this case, the attacker controls the amount of data to copy, and this essentially lets them then disclose things which are past the buffer in a packet that is being sent back. And in green, you can see the check that was eventually introduced to fix this vulnerability, but in the initial vulnerability, this check was not there. Now, a lot of different kinds of bugs fit this theme very well, so lots of different kinds of memory corruption, and as you just saw, memory disclosure bugs in C programs, buffer overflows, buffer overreads, but also this fits web applications very well. So SQL injection and command injection would be other examples. So this discussion is not so much limited to C code. Now, in our previous work at last year's conference, we presented an approach to identify different kinds of bugs, including taint-style vulnerabilities in particular. And what we did was we presented a joint data structure that we call the code property graph, and it exposes syntax, control flow, and also data flow. And the idea is to characterize bugs as traversals in this graph, so to do graph matching to find bugs. So what we did then was we took this code property graph and we put it into a graph database. And then we formulated different kinds of templates for different bugs that you could fill out to find vulnerabilities in specific code bases. Now, here's what this would look like for the heartbleed vulnerability. So you can see that I'm saying, give me all the calls to memcopy, and the third argument should be tainted by a statement that matches the regular expression dot star n to s dot star. And finally, this third argument should not be checked. Right? And this gives you kind of like a grep-like functionality, meaning that if you know what to search for, you can very quickly scan the code. Now, the problem that you have with this is that usually when you take a look at a new code base, it's a pile of garbage to you, so you really don't know what to search for in the first place. So what we want to build in this paper is more LS-like functionality, so something that will list the different kinds of programming patterns which are there in the code base in an explicit and editable form. So the question we ask is, what are the most prominent taint-style programming patterns present in the code base? Now, since this talk is limited in time and there are a lot of technical details in the paper, I just want to quickly summarize what's in there, and we're not going to talk about all of this in the talk. So the key results of the paper are we generate these queries for taint-style vulnerabilities, and these queries, they formulate rules which are explicitly contained in the code base, and the queries can find violations of these rules, so missing checks. As I already said, they are explicit and editable, so that's important. It means that all the things that can't be automatically determined from the code, the analyst has the ability to make changes to this query to fine-tune it. And on the way to do this, to generate these queries, we need to address a couple of different problems. So first of all, we extended the code property graph for interprocedural analysis, and there's a heuristic in the paper to identify library functions which are likely to modify their arguments, as for example, the N2S function that you saw earlier. There's a so-called bag of regex representation which we use, and you're going to see this in a moment, so I'm going to go into detail on this. Right, but first let's zoom out a bit and take a look at the problem. So this is the template for Taint-Style Vulnerabilities, and essentially what we want to do is we want to learn parameters of this template, so model parameters. In particular, these are the different initializations for the arguments, so what do the statements look like, and also what do the checks look like. And well, to make this very compatible with the analyst, we want these to be regular expressions, so generated regular expressions. And then once we have this, you can imagine that this program instantiated by the model parameters drives around the graph, and as it finds different matches to the query, it will output these matches as a side effect. Now, conceptually seen, this is a machine learning problem, right? So machine learning means you have data, and you have the machine learner, which generates a model for you. And then this model can be used to instantiate a predictor. And then you can throw more data at this predictor, and it will then output, well, it will, for example, put the data into groups. Now, I want to stress here that this is not, this doesn't only describe supervised learning, but this also describes unsupervised learning, as we do in with our tool. Now, learning queries is similar, so instead of the pile of garbage, we have these code property graphs that we use, that we give to the learner, and then it generates the template parameters, and these template parameters are then used to instantiate the template, and we get a program, essentially, that runs over the graph and says vulnerable or OK. Now, here's, let's take a closer look at what's inside this easy bake oven. So first of all, we assume that there's a given sink. So for example, you say memcopy. And now what it does is it starts to enumerate the different kinds of invocations. And what I mean by that is that we take a look at how are the arguments initialized, so each of them separately, and how are they validated. What we then do is we try to find similar invocations by clustering them. And that's where we use our bag of regex mapping that you see in a minute. And once we've performed this mapping, we do linkage clustering. So that's the clustering step. And then from each cluster, we can instantiate these templates and output a query where we insert the regex into this template. And we're going to talk about these steps in detail now. OK, so first of all, enumerating invocations. What I mean by invocation is if you, for example, look at the call to foo here, which is inside a function bar, you will see that bar is being called by other functions. Here it's moo and voo. And you can imagine there are different cases of initializations for the variables x, y, and z. Particularly if you do interprocedural analysis, you can get more examples of how these functions are, how the parameters are initialized. And now to enumerate all of these, we use, so the main data structure that we use here is what we call a definition graph. And it's essentially, we have a program slice for each function involved. And we take these program slices again and make a graph of these program slices that connect the slice to the slices of their callers, right? So callers are moo and voo here. And you can imagine that we can easily enumerate all of the different invocations using this data structure. So here's one, and here would be another, and there are a couple of others in there as well. Now, what we do then is we want to cluster these invocations. And to do this, we need to map them to a vector space so that we can apply linkage clustering. Now, the design of this mapping is crucial for the success of this. And this is where we introduce our bag of regex mapping. So the idea is the following. A naive mapping would simply associate each symbol that occurs in the statements with one dimension. But then something like char 52 or char 32 would be considered something completely different. Now, that's not something we want. What we want is we want similar symbols to be mapped to the same dimension. So we first cluster the symbols, and then we use the vector space that is spanned by these sets of similar symbols. Now, the nice thing is there's previous work from signature generation for malware detection that shows a nice technique where you can take sets of similar strings and then generate regular expressions from these. And so what we get is a vector space that is spanned by regular expressions. And this is how we represent the invocations that we can then cluster. Now, once we have these clusters, all we need to do is we look at the non-zero dimensions that are common among the vectors inside the cluster. And as I just said, each dimension corresponds to a regular expression. So we can simply take these regular expressions and use them to instantiate the template. Now, doing this for the sanitizers is conceptually the same. We do backward slicing to get the controlling conditions. Then it becomes a little more difficult than in the case of symbols because conditions are trees, and we need to map these trees to the vector space. But conceptually, it's exactly the same. So I'm not going into this in detail right now. All right. So of course, we need to somehow see whether this stuff works. And what we did was we had a controlled experiment where for known bugs, we wanted to see whether the system is actually capable of generating queries that express this bug. And these queries, when we execute them, they should find the vulnerable functions, and they should find very few other functions, because these will be false positives. So the core question is, does the query that we have actually reduce the amount of code that we need to review? So here's an overview of results. We used different code bases and always specified a sink. And we had, in each of these code bases, we had a vulnerability, a Taint-Style vulnerability, and we wanted to see whether we could determine the correct sources and the correct sanitizers. And in all but one case, this worked out well. And the reduction that we got was, on average, 94.9%. Now, what you can see down here is a table showing some of the regular expressions that were automatically generated by the system. You can take a look at this in the paper in detail. All right. Then, of course, we wanted to see what about the heartbleed bug? What would it generate for this? And it's nice that it actually generated this .*n2s.*, which we used in our manual query. But then it also found something else. So it found that the second argument is actually always allocated on the heaps, and there's always a check against null, right? So this the allocation in the heap shows itself in this check against null. Yeah, and then we down here we have well, the checks in there seem to always be against a number. So this is not as generic as it could be, but as I said, the analyst could now edit this string slightly to make this more generic, for example. And you see the functions that it matches. So the two functions that needed to be patched for Heartbleed are included, and there are a couple of others. But this is the entire listing, so there's not too much extra code to review. All right. Then we also wanted to see whether we can actually use this in practice to find new vulnerabilities. And well, we produced a lot of different queries, but this is one that I found particularly nice because it already encodes a bug in itself. So what you see here is that the first argument to memcopy is actually something that is allocated on the stack, and it is controlled by something that looks like a variable called len. And what that means is that you can essentially shift the stack pointer to possibly an arbitrary location in the address space to jump the guard page and essentially write to some memory to get an exploitable condition. And we reported all of these bugs, and you can see some of the CVE identifiers here, and there's also the list in the paper. Yeah, okay, that being said, I conclude what we did was we showed a system to automatically generate graph database queries from source code, and they encode Taint-style systems. Now, you can do two things with this. You can take your existing bugs and you can generate kind of like a robust signature for the bug. And the second thing is you can use this as an exploration tool. So if you look at a new code base, you can ask it, so what kind of flows are in here? How are the arguments to memcopy, for example, initialized? And conceptually seen, this is unsupervised learning of parameters for a program template, and the experiments show, well, some promising results. Now, the alternative conclusion, we created programs that take programs to generate programs that run on programs to find ways to inject programs into these programs. And also, we found something useful to do with vector spaces spanned by regular expressions. Thank you.
Can you comment on the training set a little bit more?
Can I, what?
Training set.
Training set?
Yeah.
Oh, there's not really a training set. This is, it's unsupervised learning completely. So you just take the code base, and you need to specify a sink that you're interested in, so something like memcopy. And then from that, it generates the queries. Yeah. So, yeah.
So how do you look at false positives and, you know? Do you have to manually examine the code, decide?
Well, we manually analyze the false positives. Of course, we're not entirely sure whether they're false positives, right? Because there could be bugs in there that we simply don't see. Well, I think they were all false positives. So.
Other questions? Next speaker again.